Okay, so I'll rattle through this. So in 2018, we took part in this last year, and we did badly, really badly. In fact, we deflated the average so bad that this year actually looks so much better. So the reason there's so much improvement is because we were so bad last year. I didn't do that. So what we decided was that we would take it very seriously this year, and we would try and understand memorability rather as well as trying to improve on our performance. So our interest is in getting good results and also understanding, because we've long-standing work on memory and recall. We do work on things like mind wandering and cognitive stimulation therapy and others, etc. So we took the 8,000, which are the training videos, the 2,000 which are hidden from us, and we used those, divided up into 7,000 for training and 1,000 for evaluation, and that was our own sort of in-house evaluations. And we set the task to a master's class, a taught master's class. We gave it to everybody as their assignment in machine learning. We gave it to them as their assignment for machine learning, and some of them did very well. So this is the short-term memorability. This isn't the entire class, because the entire class was 135 students. Okay, and this was their scores for long term. And you can see up at the 0.4s, there's 20 or 25 of them have got 0.4 something, so they did well. This was an exercise. They didn't care what the data was. It happened to be about memorability, but they were interested in using different forms of machine learning, from linear regression up to deep learning. So they used a wide range of techniques. They submitted a 2-page paper as their assignment for the module on machine learning, and were graded based on their approach taken and their scores. So Gautam, for example, used an ensemble approach to predict the media memorability score. Malgoratza used predicted memorability using regularized linear model and dense networks. And Aishwarya used a Bayesian model for video memorability. So correcting these was an absolute joy, okay, because you were getting so many. And the incentive for the students to do well on this was to get a good mark, but the best of those, which is the winner, not necessarily the best score, but the best overall approach, was Aishwarya. And her prize was to come here for this event. So that's a real way to incentivize your students. Anyway, so in 2019, we divided them up into 7,000 for training and validation. We developed individual models for each set of features and combined them, because our interest was on ensemble models and in combining them. And we had 130 now. It wasn't 130 because some of them didn't complete the assignment and there was only a certain number were good enough, but we learned a lot about what techniques worked well. We took 2 approaches to the ensembling. One was machine learning and standard machine learning, and the other one's using deep learning. We extracted for every one of the short videos 8 frames, which was the first and then 1 second onwards. And then we used all of these features associated with each of those frames. So we used the off-the-shelf pre-computed features that Gabby talked about. We used our own pre-computed, because we ourselves have a separate aesthetics rating for every for images, so we used that. And we also used emotions. I'll give you an example of what that is. For the captions and the text information, we used a range of things, including bag of words, TF-IDF, etc. We used our own pre-trained CNNs as feature extractors, using a form of transfer learning. So we used ImageNet, we used VGG16, we used DenseNet, ResNet. We're basically throwing the kitchen sink at it in order to generate as many possible features that we can then ensemble together. We also then did our own end-to-end fine-tuned CNN, and then we started to play with the different ensemble models and the combinations. We're very interested in emotions, and picking up what Gabby said earlier on about emotions. These are 2 videos, right? And the long-term score for this one is 0.7, right? Because, oh, he's clearly stressed about something and distressed about something, whereas for this, it's 0.2. Okay, and this was a lesson we learned from one of the submissions from last year. So the emotions that people, so first of all, as you said earlier on, or a couple of minutes ago, when people are present, they are more memorable. And when people are distressed, or showing extremes of emotion, then it's even more memorable still. So the emotions we detected were anger, disgust, fear, happiness and sadness, surprise and neutral, plus we had gender scores and the spatial information. In other words, the size of the face, in other words, how much of the screen is occupied by the face, as well as their spatial arrangement. But mostly it's the size. I was going to say the footprint of the face, but you know what I mean, it's not a footprint, right? So playing around with our validation set, we were able to determine the relative importances of things like the off-the-shelf computed features, our own features, the captions and the textual information, the pre-taint, which is just basically identifying content, and then our own CNN. So this gave us an inkling on what were more or less important among those features. And our official performance figures, this is on the test set, so this is the numbers that you showed up earlier, and this is on our validation set. And again, there's not much difference between those as a set and between those as a set, but there's a bit of a difference between that, because we're training on 7,000 and testing on 1,000. We're training on 8,000 and testing on 2,000. And that's our short term and our long. And the variations between them, they're just variations on the ensemble combinations. They're variations because they use different relative weightings for different kinds of ensembles. So this is ensemble number 1, 2, 3, 4, and 5, and these are the relative weights for things like the content, the captions, the emotions, the aesthetics, and other low-level features. What do we learn from this? Well, as you had pointed out, the deep learning models typically outperform models which are trained with captions and other visual features for short term, but techniques such as embeddings and recurrent neural networks can achieve high results for captions. So they kind of complement each other, which speaks to ensembling. We believe that the fine-tuned CNN models will outperform the trained models. Ensembling models by using predictions instead of training models with long vectors is a way to make it all computable and addresses memory limitations. And as you said, just echoing it, ensemble models with different modalities, in other words, emotions, captions, people, faces, all of that sort of stuff, tends to perform better. The most interesting thing, so this is the visualizations, the word clouds associated with captions. The most interesting slide I hope you'll see is this one here. So what we did for the high scoring ones was we used class activation maps for the most memorable videos. And this is a heat map which shows which parts of the video led the CNN to rate it highly. Now this isn't a proxy for people remembering, but this is the work we're interested in. This is more than just a machine learning task to see you can bash and get the best set of hyperparameters to score. What our interest is in looking beyond that and seeing what is more memorable. So this sets us up to take this very memorable video and to see which parts of it make it more memorable. And that's it. All of our stuff, by the way, the code and everything else is available on the GitHub repository, which is linked to from the paper. Any questions?